Yellow light from a certain lamp has a wavelength of 582 nanometers, and we are asked to determine the energy and the frequency of the light. How would it compare to orange light, and how would it compare to blue light? So a particular lamp has yellow light coming from it, and recall that the color of light is determined by how far the electrons fall, because that gives off a certain amount of energy with a certain wavelength. And remember that photons are the wave particle quantum objects that have both wave function and particle, for wave behavior and particle behavior. When an electron falls from a higher energy state, so here's an example of like an energy ladder. It is not to scale, but if an electron falls, so I was going to say energy on the left. If an electron falls from a high level down to a lower level, like from an excited state to a ground state, for example, it'll release a certain amount of energy in its fall. And the energy it releases will be in the form of a wave, and it'll have a certain wavelength, which is lambda. Always needs to be in meters. And of course it'll have a certain energy, a certain frequency, which sometimes is seen as nu. And we can determine these things just based off of one of the pieces of information, as long as you remember that Planck's constant is a number that relates frequency of a wave to energy of a wave, and that is 6.626 times 10 to the negative 34th power. And the units are joule seconds, joules times seconds. It's a derived unit. And then c is the speed of light in a vacuum, which is 3.0 times 10 to the 8th power, and it's meters per second because it's a speed over a time, which is a rate or velocity or speed. So we can get started with this problem, and I'll be doing it live with you. So we have the wavelength of this light, and we know that it is 582 nanometers. 582 nanometers is a useful way to say it or represent it, because nanometers, 1 nanometer is 1 billionth of a meter. And because waves, especially visible light waves, have really tiny wavelengths, their photons have tiny wavelengths, nanometers are more useful to say, but we know that we need to work with it in meters because of this part right there. We know that speed of light is in meters per second, not nanometers per second. That's the standard rate unit. So I'm going to remind myself of the two equations that would help me out. E equals hf, or h nu, depending on the book or the class. And I also know that c equals lambda, which is a wavelength, times the frequency of the light. I'm given the wavelength, which means that I will not be using the first equation first. I'll be using this equation first. So if I'm going to plug this, I'm actually going to rearrange this right now. I'm going to solve for frequency to remind myself that this would turn into frequency equals c over lambda. I know the speed of light, and I know the wavelength of that light, but the wavelength is not quite in the unit I want it in. But even then, I'm going to substitute this equation into, or I'm going to substitute the equation as it represented by what f is equal to, which is c over lambda, into where f is in the first equation, because I want to find the energy and also the frequency. And I'll be killing two birds with one stone when I do that. Let's first find the frequency of the light. And I guess I'll say this now, there are multiple ways to do this. I could find the frequency, which is what I'm doing right now, based off of the speed of light and the wavelength, and just use that in the first equation, which is E equals hf. Or I could just substitute and get the derived equation, which is E equals h times c over lambda. Either are fine. So let's do the first. Let's actually just solve it in that order. Frequency equals c over lambda, which is 3 times 10 to the 8th power in meters per second, divided by the wavelength, which is not in the correct unit. So let's actually solve this problem right now, because we want our wavelength in meters in order to get frequency. And we don't have meters, we have nanometers. So if we address this issue, I know that 582 nanometers is given to me, but I do not want nanometers. I want meters. So I'm going to do a conversion. Nanometers to meters. I want my nanometers to cancel out. 1 meter contains a billion nanometers, because from your prefixes in the earlier part of the class, you remember that nano means billionth. So a billion nanometers goes in a meter. That's 1 times 10 to the 9th power. When I do the math for this, I get 582 divided by 1 times 10 to the 9th. And I find out that 582 nanometers is equal to 5.82 times 10 to the negative 7th meters. So that's what I'm going to put that here. 5.82 times 10 to the negative 7th meters. And you'll see that my meters will cancel, giving me an inverse second, which is my frequency. So 3 times 10 to the 8th, that's the speed of light, divided by the frequency, divided by the wavelength in meters, which is 5.82 times 10 to the negative 7th, gives me a frequency of, so frequency, I'll just put that here. The frequency is 5.15, and then some other digits, times 10 to the 14th, and the units are hertz, which we know is an inverse second, so I'm just going to put HZ for the hertz abbreviation. I've actually found the frequency already, and I can use that and plug that into the first equation to find the energy. So let's remind ourselves what the first equation is, and it's written up there. E equals HF. The energy of that light is equal to Planck's constant, which is 6.626 times 10 to the negative 34th, times the frequency, which is 5.15 times 10 to the 14th hertz. So I'm going to multiply them together, and I'm doing this right now, 6.626 times 10 to the negative 34, and that gives me an energy of 3.4, we'll say 2 times 10 to the negative 19th power, and it's energy, so our unit is in joules. That's how much energy a single photon has of that red light, of this yellow light. That's how you would do one of those problems. Now I will show you really quickly another method that some people prefer, and that is the purely substitution method. Just as a reminder, it is E equals HF, and we've already solved for what F is equal to from the speed of light times, equation. Frequency equals the speed of light divided by the wavelength. You could combine these two equations together to get E equals H times C, which is a constant in itself, divided by lambda. If you were to solve it this way, you have 6.626 times 10 to the negative 34 times speed of light, which is 3 times 10 to the 8th. Remember, that's what E means, times 10 to the. It's a shorthand method. All divided by the wavelength, still in meters, which is 5.82 times 10 to the negative 7. And you can do your math this way, but you have to be careful to use your parentheses and such appropriately. And you'd still get that same answer. So that is how you would tackle a problem that's giving you the wavelength, and you must find the energy and or the frequency. And the same logic applies if you're given the energy and you must calculate, for example, the wavelength. it could be useful to first calculate this frequency given the energy, and then use the frequency and the speed of light to calculate this. Those are just algebra skills. If you don't remember how to rearrange or substitute, you should review that. But the logic applies regardless of if you're going from wavelength to energy or energy to wavelength or using frequency somewhere in between. This is the most advanced type of problem you would see for this. You're not calculating the number of photons or the moles of electrons or anything like that in this level.